Hello everyone, it is Buket from ICHEC. This is a short introduction to the new features of OpenMP after version 2.5. In this presentation, I will be talking about the topics listed in the outline. First, I am going to summarize the new features of OpenMP introduced from version 3.0 to 5.0. Then, I am going to describe task-level parallelism, improvements to nested and loop-level parallelism, and some additional environment variables in version 3.0. Then I will discuss the new features introduced in version 3.1 and talk a little bit about the new clauses and constructs. After that, I will define the new SIMD construct and extensions to the reduction clause. Then I will mention additional features in version 4.0, such as Accelerator and error model. At the end of the presentation, I will list some of the proposed features of version 5.0. Version 3.0 was released in May 2008 with new features including tasks, and a better support for loop-level and nested parallelism. Addition of tasking is the biggest change between 2.5 and 3.0. With this new feature, a wider range of applications can now be parallelized. The collapse clause is added to the loop and parallel loop directives to allow parallelization of perfect loop nests. The auto clause is added to provide full freedom to the runtime to determine the scheduling of iterations in a loop. Moreover, there are several new clauses, runtime functions, and environment variables. The next version, version 3.1, was released in July 2011. Several important items led to this new version, as well as improvements to task-level parallelism. There is also an initial support to thread affinity. OpenMP 4.0 Release Candidate 1 was released in November 2012. It includes SIMD constructs to vectorize both serial and parallelized loops, thread affinity, a new tasking construct, initial support for Fortran 2003, and user-defined reductions. The release candidate 2 was released in March 2013. In addition to a number of corrections and clarifications to the previous release, it includes several new major features, such as initial accelerator and error model support. The OpenMP Architecture Review Board plans to finalize 4.0 API specifications later this year. They plan to work immediately after on OpenMP 5.0. Earlier versions of OpenMP focused on data parallelism. After 3.0, task parallelism is introduced for the applications that don't exhibit data parallelism and that can benefit from the dynamic generation and scheduling of tasks. OpenMP has always had tasks, but they were never called with a separate task construct. Version 3.0 simply adds a way to create a task explicitly for the team threads to execute. This new feature allows parallelizing irregular problems, unbounded loops, recursive algorithms, multi-block grids, and many others. Essentially, a task is a work unit which may be executed by the encountering thread or deferred for execution by any other thread in the team. It is composed of a code block to execute, data environment, and internal control variables initialized at the creation of the task. A task is generated each time a thread encounters a task directive. Each encountering thread packages a new instance of a task. Some thread in the team executes the task at some later time. The thread that executes the task is called task thread. The task thread may be the encountering thread or any other thread in the encountering threads team. The task directive instructs the compiler to run a block of code in parallel with the code outside the task region. It is defined by pragma OMP task in C++, OMP task in Fortran. In particular, OMP and task is used to enclose the tasking region in Fortran. Curly brackets are used in C++. Clauses are if, untied, and data clauses. A task is tied by default. This means that the same thread from beginning to end will execute the code associated with the task construct. You can use the untied clause in order to specify that different threads execute different parts of the code. When the if clause is used and when it evaluates the false, the task is executed immediately by the encountering thread. The data environment of the task is created according to the data sharing attribute clauses on the task construct and any defaults that apply. A shared variable refers to the variable with the same name known immediately prior to the task directive. A first private variable is initialized with the value of the original variable at the moment the task is created. For each private and first private variable, a new storage is created and all references to the original value in the lexical extent of the task construct are replaced by references to the new storage. If there is no default clause, a variable that is not listed in any data sharing attribute clauses is determined to be shared if it is shared in all enclosing constructs up to and including the innermost enclosing parallel construct. Otherwise, it is implicitly determined to be first private. Nesting of tasks is permitted. In other words, a task may itself generate other tasks. Moreover, tasks can be nested inside parallel regions and work sharing constructs. Task synchronization is provided by the task wait construct. The current task region is suspended at this point until execution of all its child tasks generated before the task wait region are completed. If the suspended task is tied, then the same thread later resumes execution of the suspended task. If the suspended task is untied, then any thread in the current team may continue the task execution. The default task behavior is the same as for task wait. Moreover, all tasks created by any thread of the current team are guaranteed to be completed at the barrier exit. There exists an implicit barrier at the end of the structured block for parallel and any work sharing construct. We illustrate a simple example of task synchronization on the right. First, n tasks are created with the pragma OMP task, one for each thread. After the pragma OMP barrier, all tasks are completed. Then, one task is created in a single region. At the end of the single region, the task is completed because of the implicit task wait. We next consider generating the Fibonacci sequence by using the OpenMP tasking model. By definition, the first two numbers in the Fibonacci sequence are 0 and 1, and each subsequent number is the sum of the previous two. Thus, the sequence fib_n of Fibonacci numbers is defined by the recurrence relation. In the main program on the left, we first create a parallel region, which will be executed by 4 threads. In the parallel region, the single directive is used to indicate that only one of the threads will execute the print statement that calls the function fib_n. The call to fib_n generates 2 tasks indicated by the task directive. One of the tasks computes fib_n-1 and the other computes fib_n-2. and the return values are added together to produce the value returned by fib_n. Each of the calls to fib_n-1 and fib_n-2 will in turn generate two tasks. Tasks will be recursively generated until the argument passed to fib_n is less than 2. The task wait directive ensures that two tasks are completed before that invocation of the fib function returns. Note that although only one thread executes the single directive and hence the call to fib_n, all four threads will participate in executing the tasks generated. Recall that OpenMP allows parallel regions to be nested inside each other. Using either a runtime library function or an environment variable should enable this. However, support for the nested parallelism is implementation dependent. There is a better support and improved features in version 3.0 with new runtime library functions, environment variables, and internal control variables. New environment variables and library routines are added to control the maximum number of active parallel regions and OpenMP threads, and to get information about nested parallelism. We list some of these here. The OMP max active levels environment variable controls the maximum number of nested active parallel regions. Its value must be a non-negative integer, and the behavior of the program is implementation defined. The OMP set max active levels routine limits the number of nested active parallel regions, while the OMP get max active levels routine returns its value. The OMP thread limit environment variable sets the number of OpenMP threads to use for the whole OpenMP program. The value of this environment variable must be a positive integer, and the behavior of the program is implementation defined. The OMP get thread limit routine returns the maximum number of OpenMP threads available to the program. The OMP get level routine returns the number of nested parallel regions enclosing the task that contains the call. The OMP get active level routine returns the number of nested active parallel regions enclosing the task that contains the call. The OMP get ancestor thread num routine returns the thread number of the current thread for a given nested level of the current thread. The OMP get team size routine returns the size of the thread team to which the current thread belongs for a given nested level of the current thread. Recall that internal control variables control the behavior of an OpenMP program. These variables store information such as the number of threads, whether nested parallelism is enabled or not, or the scheduling type for the loop level parallelism. There are additions to the control variables in version 3.0. One of them allows setting the number of threads inside a region to control the team size for the next level of parallelism. In version 2.5, there was a single copy of numThreads internal control variable for the whole program. Now, each region can have its own behavior. In the example, we set numThreads to 3 at first, then we change its value to 5 for the next parallel region. Recall that loop-level parallelism provides loop iterations to be distributed over the threads. There are improvements to loop-level parallelism in version 3.0, as well as new clauses and environment variables. When static scheduling is specified, iterations are first divided into chunks of specified chunk size, and then chunks are assigned to threads in the team in a round-robin fashion in the order of the thread number. The assignment of iterations to threads can be ensured to be same across multiple loops in the same parallel region if and only if the number of iterations is equal and the chunk size is same. Another scheduling type for the loop construct is runtime. Iterations are set at runtime through the environment variable OMP schedule. It is now possible to set or get the runtime scheduling with the library routines OMP set schedule and OMP get schedule. A new scheduling type called auto is added in version 3.0. It gives implementation freedom to choose the best mapping of iterations to threads. The compiler or runtime system decides what is best to use. It could be implementation dependent. There is a new clause called collapse for the loop construct in version 3.0. The collapse clause is used to parallelize perfectly nested multidimensional loops without using the nested parallelism. It takes a constant positive integer as a parameter, which determines how many loops are collapsed. Compiler then forms a single loop and parallelizes it. There are additional environment variables in version 3.0. For example, OMP stack size is used to control the size of child threads stack. The default unit for the stack size is kilobytes. OMP wait policy controls thread's idle behavior. Active mode keeps thread alive at barrier or locks, while passive tries to release processor and avoids the use of CPU. Moreover, there are minor fixes and clarifications to data environment, clearer rules for how private objects are constructed, and relaxed restrictions on Fortran arrays and pointers. See the OpenMP specification for more details. In version 3.1, there are several clarifications and improvements to the version 3.0 and a couple of new features. We will briefly go through some of these. First of all, the atomic construct was extended to include read, write, and capture forms, and an update clause was added to apply already existing form of the atomic construct. Data environment restrictions were changed to allow intent in and const qualified types for the first private clause. New reduction operations such as min and max were added for C and C++. Initial support for binding of threads to resources is introduced. OMP proc bind environment variable is added to control whether or not threads are bound to processors. Specifically, if it is set to true, OpenMP threads don't move between processors. Task yield construct is added to the tasking model. It allows you to define task switching points by suspending the current task in favor of the execution of other tasks. The final and mergeable clauses are added to the task construct to support optimization of task data environments. In order to understand these clauses, let me explain some concepts in the tasking model. An undeferred task is a task for which execution is not deferred with respect to its generating task region. In other words, the generating task region is suspended until the undeferred task has finished running. It is generated when an if clause is specified on the task construct and it evaluates to false. An included task is an undeferred task that is sequentially included in the generating task region. In other words, included task is undeferred and executed immediately by the encountering thread. A merged task is a task that has the same data environment as that of its generating task region. It might be generated when a mergeable clause is specified on a task construct, or the generated task is an undeferred task or an included task. A final task is a task that forces all its child tasks to become included tasks. If the expression evaluates true, it specifies that the generated task will be a final task. All task constructs encountered during execution of a final task will generate included tasks. There is also a new runtime function called OMP in final. It returns true if the routine is executed in a final task region. Now we will talk about the features introduced with both release candidates of version 4.0. The most important ones are addition of the SIMD construct, extensions to reduction clause, and a new accelerator model. The SIMD construct enables the execution of multiple iterations of the associated loops concurrently by means of SIMD instructions. In other words, in a single instruction, multiple data sends. Each concurrent iteration is executed by a different SIMD lane. If more than one loop is associated with the SIMD construct, then the iterations of all associated loops are collapsed into one larger iteration space that is then executed with SIMD instructions. Classes of the SIMD construct are safe-len, linear, aligned, private, last private, reduction, and collapse. They control how loop iterations are partitioned. The safe-len clause limits the number of iterations in a SIMD chunk. Its parameter must be constant positive integer. The linear clause lists variables with a linear relationship to the iteration space. Align declares one or more list items to be aligned to the number of bytes expressed in an optional parameter. Other clauses have usual meanings. The declare SIMD construct can be applied to loops that include a C, C++, or Fortran function, or a Fortran subroutine to concurrently execute using SIMD instructions. The safe-len clause specifies the number of concurrent arguments for the function. The uniform clause declares one or more arguments to have an invariant value for all concurrent invocations of the function. The in-branch clause specifies that the function will always be called from inside a conditional statement of a SIMD loop. Not in branch specifies that the function will never be called from inside a conditional statement of a SIMD loop. Others are similar to the SIMD construct clauses. In the example above, we tell compiler to generate SIMD version of the min function. The next SIMD construct is the loop SIMD construct. It specifies a loop that can be executed concurrently using SIMD instructions, and that those iterations will also be executed in parallel by threads in the team. The loop SIMD construct will first convert the associated loops to a SIMD, then the resulting SIMD chunks and any remaining iterations will be distributed across the implicit tasks of the parallel region. Clauses can be any of the clauses accepted by the for or SIMD directives with identical meanings. In the example below, we calculate the minimum of two vectors in entry-wise in a SIMD loop instead of classical parallel for loop. User-defined reductions are major addition in OpenMP 4.0. So far, OpenMP has only supported reductions for basic data types and a limited set of C, C++, and Fortran operators. With this new feature, OpenMP now supports reduction for user-defined data types. Use declare reduction directive to declare user-defined reductions. Here, the reduction identifier gives a name to the operator. It is either a base language identifier or a user-defined operator. It is used in a reduction clause using variables of the type specified in the directive. In the example below, the identifier merge is used in the reduction clause as a reduction operator applied to the list variable filtered. Combiner in the declare reduction directive specifies how to combine private copies of the list variable into a single value. OMP auth refers to private copy that holds the combined value. In other words, it refers to the storage that holds the resulting combined value after executing the combiner, while OMP in refers to the other private copy. Version 4.0 adds the task group construct to support simpler task synchronization. It has a similar effect to task wait construct. Current task is suspended until all child tasks generated in the region complete execution. Another new extension in version 4.0 is additional support for thread affinity. The new clause procbind is included to the parallel construct to specify the places to use for the threads in the team within the parallel region. The value is among, master, clause, or spread. The master thread affinity policy assigns every thread in the team to the same place as the master thread. The clause policy assigns the threads to places close to the place of the parent thread. The purpose of the spread policy is to create a distribution for a team of threads among given places of the parent's place partition. The OMP procbind environment variable is extended in version 4.0. It could specify true or false in version 3.1. It can now provide master, clause, or spread thread affinity policy to be used for parallel regions at the corresponding nested level. The new OMP places environment variable specifies a list of places for thread binding. This can be threads, cores, or sockets, or an explicit list of places described by non-negative numbers. There is also a new runtime library function, OMP get print. It is used to get the current thread affinity policy to be used for the next most closely nested parallel region. We will now briefly talk about the initial accelerator support in OpenMP introduced with the release candidate 2 of version 4.0. It is supported by target constructs that control how data and code are offloaded to the device. They create device tasks that are executed by devices. A device has a data environment. Variables are copied in and out of a data environment or shared with the host. The target construct is the main construct. Clauses are if, device, and map. When there is an if clause and it evaluates to false, the target region is executed by the host device. The device name is specified in the device clause. If there is no device clause, it is determined by the default value of the internal control variable associated with the device. The map clause maps a variable from the current task's data environment to the device data environment associated with the construct. The map type determines how new list item is initialized. The alloc map type declares that on entry to the region, each new corresponding list item has an undefined initial value. The toMap type declares that on entry to the region, each new corresponding list item is initialized with the original list item's value. The fromMap type declares that on exit from the region, the corresponding list item's value is assigned to each original list item. The two fromMap types combine the functionality of both to and from types. For list items in the map clause, corresponding new list items are created in the device data environment associated with the construct. In the illustration below, you can see that the dot product is offloaded to the device ACC0. If a map type is not specified, the default value is toFrom. The target data construct creates a device data environment for the extent of the region. Clauses are same with the target construct. Note that the list items that appear in a map clause may include array sections, as you can see in the example. The target update construct makes the corresponding list items in a device data environment consistent with the original list items according to specified clauses. It updates a variable from the data environment of the current task to the enclosing device data environment, or vice versa. For each list item in a to clause, the value of the original list item is assigned to the corresponding list item. For each list item in a from clause, the value of the corresponding list item is assigned to the original list item. The device is specified in the device clause. When the if clause evaluates to false, then no assignments occurs. The declare target construct can be applied to a function in C, C++, and Fortran, or a Fortran subroutine to enable the creation of a device-specific version that can be called from a target region. Some runtime library functions and an environment variable associated with the Accelerator model are listed here. The OpenMP set default device routine assigns the value of the default device internal control variable. The OpenMP get default device routine returns the value of the default device internal control variable. The OpenMP get num devices routine returns the number of target devices. The OpenMP default device environment variable sets the device number to use in a target construct by setting the initial value of the default device internal control variable. It must be a non-negative integer value. As a final section, we will briefly introduce initial error model support. The error model requests cancellation of specified region types or declares a defined cancellation point to check for cancellation requests. The cancel construct asks cancellation of the innermost enclosing region of the type specified. When it is used for a parallel, sections, for, or do region, each thread of the binding thread set continues execution at the end of the cancelled region. When it is requested through the cancel task group construct, the innermost enclosing task group will be cancelled. When an if clause is used and it evaluates to false, the cancel construct doesn't request cancellation. The cancellation point construct corresponds to a user-defined cancellation point at which an implicit or explicit task must check if cancellation of the innermost enclosing region has been requested. The OpenMP cancellation environment variable sets the initial value of the cancellation internal control variable. The value of this environment variable must be true or false. If it is set to true, the effects of the cancel construct and of cancellation points are enabled and cancellation is activated. If it is set to false, cancellation is disabled and the cancel construct and the cancellation points are effectively ignored. Finally, here is a very brief list of proposed features in version 5.0. These are improvements to thread affinity and support for memory affinity, refinements to accelerator support, additions to task-level parallelism, and completing Fortran 2003 integration. These are the references used to prepare this presentation. Thank you for your attention.